Section 6.4, volume by shells. This technique will help us to find the volume of revolution when we rotate the area bounded by the graphs about the axis of revolution. We will look at the slice within the region and rotate about the axis of revolution. It will form the shell, the cylindrical shell. Then we're going to find the volume of each shell. Add them all up. Using the Riemann sum, it will form the definite integration to provide you the volume of this solid of revolution. Let's look at the case here. In the case that the function f is greater than or equal to function g, and the R is the region bounded by these two graphs from point A to point B, we rotate this region about the y-axis. To find the volume of the solid of revolution, we consider one slice within that region, and this slice is perpendicular to the axis of revolution. Rotate about the y-axis, it will form the cylindrical shell. Then we're going to find the volume of this single shell. If we cut the edge and open it up, it will form the rectangular solid shape. The volume of this shape is the length times the width times the height, and the width is delta x, which is from the thickness of the slice that we considered before we revolve about the y-axis. And the length is from the circumference of the shell, or 2 pi r. And in this case, the r is measured from the axis of revolution. And also the height of the bar is the difference of two functions. Therefore, the volume of the solid of revolution is the definite integral from A to B of 2 pi r h and dx. This 2 pi r as the circumference of the shell height, and the thickness delta x. So to find the volume of revolution, we need to know the position, the thickness, the height, and also you find the interval of integration with respect to x or with respect to y. The first example, use the shell method to find the volume of the solid of revolution generated when the region bounded by the following curves is revolved about the given axis. In part A, y equals x minus x squared, y equals 0, and rotate about the y-axis. From the graph provided, y equals x minus x squared is the parabola opens down with the intercept at 0 and 1. To rotate about the y-axis, we form the shell or one slice parallel to the axis of revolution. And this is the position x with the thickness delta x. And the axis of and the interval of integration will be x greater than or equal to 0, less than or equal to 1. When it rotates about the y-axis, it will form the cylindrical shell. So we're gonna need the radius of the shell. The radius would be the measurement from the axis of revolution to that position of the shell, which is the x. So r equals x. And the height of the shell is the height of the function value. So the height is the y, or x minus x squared. Now we put them together. The volume equals the interval from A to B. 2 pi, the r or the radius would be x, the height or the function value would be x minus x squared. And the thickness is dx, which is from delta x. Simplify the integration. Take the 2 pi out of the integration and multiply x to x minus x squared. We have x squared minus x to the third with respect to x. Find the antiderivative will give us x to the third over 3 minus x to the fourth over 4. In our case, the a is 0 and the b is 1. 0, 1. Next, replace the value of the upper limit and lower limit to find the final solution. So 1 over 3 minus 1 over 4 from substituting the upper limit and subtracted by 0 minus 0 from using the lower limit. Therefore, the final result would be pi over 6. Let's look at another example. Y equals 12x. That's the line with the slope 12. Y equals 12. That's the horizontal line. X equals 0 is the y-axis and rotate about the y-axis. When we put all these three graphs together, we should get the triangle. Look, the line y equals 12x, y equals 12, and x equals 0. And this region rotate about the y-axis. Recall, we're gonna form the slice parallel to the axis of revolution. And this position is the position x with the thickness delta x or dx that we're gonna use as part of the integration. For the delta x is dx and the position x, the interval of integration will be from 0 to 1 because the intersection point here at 1, 12. To rotate about the y-axis, it should form the shell that looks similar to this. So set up the integration. The volume V is the integral from a to b, or from 0 to 1, 2 times pi times the radius. In this case, the radius is the measurement from the axis of revolution to the position of the slice. The radius is x. And the height is the length from the top of the bar to the bottom of the bar, which is the difference of the upper function, or y equals 12, and the lower function, which is 12x. And the thickness is dx. I'm going to put a note here. The radius is x. The height is 12 minus 12x. And the thickness, or the width, is dx. We're done setting up. Next, we're going to clean up and find the antiderivative. Factor the 2 pi out. And we can see the common factor 12 as well. So take the 12 out from 0 to 1 and multiply x to the parentheses. We should get x minus x squared with respect to x. And v equals 24 pi. Antiderivative of the x is x squared over 2. Antiderivative of x to the second is x to the third over 3. Evaluate from 0 to 1. Use the upper limit. We have 1 over 2 minus 1 over 3 minus 0 from the lower limit. And then the answer will be 4 pi.